So let's do some more problems with gas law problems. Again, one of the trickiest parts of gas law problems is identifying which appropriate gas law equation is helpful for the problem. So this problem reads, a piston holds 100 liters of gas at a temperature of 2000 degrees Celsius. It is then cooled until the gas volume is 75 liters. What will the final temperature of the gas be? So once again, let's sort of look and see what we have here. 100 liters, that's a volume. At a temperature of 2000, that's a temperature. Is cooled, so I have a change in process until the gas volume is 75 liters. So again, they're telling me another volume, so I have two volumes, and they're asking what will the final temperature be. So they're I want a second temperature. So we have two volumes and two temperatures being compared in this. I may recognize right off that's Charles. I may have to use my combined gas law and figure out which equation to use. All right, let's just write down what we have. V1 is 100 liters. T1 is 2000 centigrade. And I'm going to go ahead and convert that to Kelvin. That's 2273 Kelvin. My other volume is 75 liters. And my final temperature is the thing that I'm trying to find. Okay, so again, one strategy is to use the combined gas law. P1 V1 over T1 equals P2 V2 over T2. And in this case, pressure is constant. So I'm really just dealing with V1 over T1 equals V2 over T2. This would be Charles' law, by the way. Okay, so let's fill in what we have. We have 100 liters over 2273 Kelvin is equal to 75 liters over T2. Now, I'm going to use some cross-multiplying. If we don't remember what cross-multiplying is, I'm going to have an issue when the thing that I'm solving for, in this case T2, is in the denominator of the fraction. And so in order to get it out of the denominator, I'm going to do some rearranging. So I'm going to multiply both sides by T2 and by 2273. Do it on the other side, 2273 Kelvin times T2. And rearranging, I have 100 liters times T2 equals 2273 Kelvin times 75 liters. Note that if I divide both sides by 100 liters, it cancels and I'll be left with T2 on the right, which is what I want to do. I want to isolate my variable I'm trying to solve for. I have to do it to both sides of the equation. So I get T2 is equal to 2273 Kelvin times 75 liters divided by 100 liters. Note that my liter units will cancel out, and I will be left with 1705 Kelvin. That's how we solve that problem.